students. So we started with the topic 8086 microprocessor, and in that topic we discussed till the execution unit, where we discussed about the general purpose registers. That I've told you that execution unit consists of general purpose registers, flag registers, pointer and index registers. So in the last class I discussed about general purpose and pointer and index registers. So the next parts of the execution unit I'm going to discuss in this lecture. So the next part is flag register. So a flag is a flip-flop which indicates some condition produced by the execution of an instruction or controls certain operations of the execution unit. So this flag register contains it's obviously a 16-bit flag register, and 9 of the 16 are active flags and remaining 7 are unidentified. So these 9 active flags, among these 9 active flags, 6 flags indicate some conditions, that is they are status flags, and among the 9 flags, 3 flags are the control flags. So let's first discuss the 6 flags, that is 6 status flags. So starting with the carry flag, the 6 status flags are carry flag, parity flag, auxiliary flag, zero flag, sign flag and overflow flag. So carry flag, what happens in case of addition? This flag is set if there is a carry out of the most significant bit. So the carry flag also serves as a borrow flag for subtraction. In case of subtraction, it is set when borrow is needed. Next is parity flag. It is set to 1 if the result of byte operation or lower byte of the word contains an even number of ones, otherwise it is 0. So next is auxiliary flag. Auxiliary flag is set if there is an overflow out of the bit 3, that is carry from lower nibble to the higher nibble. This flag is basically used for BCD operations and it is not available for the programmer. The next is zero flag. The zero flag is set if the result of operation in ALU is 0, and flag resets if the result is non-zero. The zero flag is also set if a certain register content becomes 0 following an increment or decrement operation of that register. Next is sign flag. So after the execution of arithmetic or logical operation, if the most significant bit of the result is 1, the sign bit is set. Sign bit 1 indicates the result is negative, otherwise it is positive. And the last one is overflow flag. This flag is set if the result is out of range. For addition, this flag is set when there is a carry into the MSB and no carry out of the MSB, or vice versa. For subtraction, it is set when the MSB, that is most significant bit, needs a borrow and there is no borrow from the MSB, or vice versa. So let's take an example to understand all these flags. So suppose if the register AL content is 7FH, so if you write 7F in terms of binary, it will be 0 1 1 1 1 1 1 1, and the instruction add AL1 is executed, then the following happen. So what happens if you add 1 to the content of accumulator low? If you add 1, then what you will get? The result will be 1 0 0 0 0 0 0 0. So okay, the result will be 80H. This is 8, this is 0. So as you can see, there is no carry out of the most significant bit, so it will be in its status will be 0 after the execution of this instruction, that is after arithmetic operation. What will be the status of flags that I am trying to discuss here? So after adding 1, that is after having an arithmetic operation, the result is 80H, and depending on that, what are the status of flags? Carry flag will be 0 as there is no carry out of bit 7, that is 0, 1, 2, 3, 4, 5, 6, 7. Out of the bit 7 there is no carry. Parity flag is 0 because this whole 80H is having odd number of ones. If it had been even parity, then the parity flag would have been set, parity flag would have been 1. For even parity, parity flag is 1. For odd parity, parity flag is 0. So here the parity is odd, so parity flag is 0. Auxiliary carry flag is 1, as there is carry out of bit 3. After during the addition operation, what is happening? Out of the bit 3, there is a carry into the bit 4. So auxiliary carry flag will get set. Zero flag is 0 because the result is not 0. Sign flag is 1, as bit 7 is 1, as the bit 7 is 1. And auxiliary carry flag is 1. Why? Because the sign bit has changed. As you can see, the sign bit, that is the most significant bit, is changed. Or you can say during the addition operation, what happened for addition operation, there is a carry into the MSB. The carry was into the MSB, but there was no carry out of the MSB, so the overflow flag will get set. Okay, these were the 6 status flags. The remaining 3 flags, which are control flags, they are trap flag, interrupt flag, and directional flag. So what is the purpose of trap flag? One way to debug a program is to run the program one instruction at a time and to see the contents of used registers and memory variables after execution of every instruction. So this process is called single stepping through a program. So trap flag is used only for single stepping through a program. If the trap flag is set, a trap is executed after execution of each instruction, that is, interrupt service routine is executed, which displays various registers and memory variable contents on the display after execution of each instruction. Thus, programmer can easily trace and correct errors in the program. The next is interrupt flag. Interrupt flag is used to allow or prohibit the interruption of a program. If set, a certain type of interrupt can be recognized by the 8086 microprocessor. Otherwise, these interrupts are ignored. And the last one is direction flag. It is basically used with string instructions. If direction flag is 0, the string is processed from its beginning with the first element having the lowest address. Otherwise, the string is processed from the high address towards the low address. So this was all about the flags of the execution unit. So the next topic is bus interface unit. As I have told you that bus interface unit consists of 6-bit instruction queue. It contains segment registers, instruction pointer, and then address summing block. So starting with the 6-byte instruction queue, what is the purpose of 6-byte instruction queue? Basically, what happens to speed up program execution, the bus interface unit fetches 6 instruction bytes ahead of time from the memory. These prefetched instruction bytes are held for the execution unit in a group of registers called queue. With the help of queue, it is possible to fetch next instruction when current instruction is in execution. For example, current instruction in execution is a multiplication instruction. In 8086, operands for multiplication instruction are within the registers. Still, it requires 100 clock cycles to execute multiply instruction. Like multiplication, there are number of other instructions in 8086 which needs a large number of clock cycles for execution. During this execution time, the bus interface unit fetches the next instruction or instructions from the memory into the instruction queue instead of remaining idle. The bus interface unit contains this process as long as the queue is not full. Due to this execution unit gets the ready instruction in the queue and instruction fetch time is eliminated. The queue operates on the principle first in, first out, so that the execution unit gets the instruction for execution in order they are fetched. In case of jump and call instructions, instruction already fetched in queue are of no use. Hence, in these cases, queue is dumped and newly formed by loading instructions from the new address specified by jump or call instruction. Feature of fetching the next instruction while the current instruction is executing is called pipelining. So this was all about instruction queue. Next we are going to discuss about the segmented memory. In my next lecture I am ending this class here. Thank you.